Okay, I know that this is a unit that you guys have already kind of talked about a little bit in Algebra 2 and probably even in Algebra 1, but functions are very important for what we are going to do and for moving into calculus. So we're going to kind of drill that at the beginning. So in this section, we're going to figure out if a relation is a function. We're going to evaluate functions. We're going to find the domain of functions, and we're going to evaluate something that's called a difference quotient. Hopefully we'll be able to get through a lot of these things today. We'll see how far we get. Again, I'm not quite sure. So what is a relation? A relation is a rule or connection between two different quantities. So an example of a relation is the area of a circle is related to its radius, and there's even a formula for it. There's not always a formula for every relation, but in this case there is. Another example, the time of day is related to the temperature. They're related, they're connected, because at a particular time of day, there is a temperature that is related to it, that is associated with it, that we could measure, right? Not all relations have nice mathematical formulas. For example, like the radius of the area and the radius of a circle, that has a nice formula. Temperature and time of day, that doesn't really have a nice formula for it. I'm going to click to present this. Okay, so what do relations look like? Relations can look like this, where they are mappings. We have one set here, and then another set here, and there's literally a line. Sometimes it's an arrow that shows the connection between the numbers. So the number -9 is related to 1. They could be a table, where we have an x and an f of x, an input and an output. So -4 is related to 0, 2 is related to 2, so on. They could be a graph, which is really just kind of a visual representation of a table. They could be a set of ordered pairs, which is sort of like a table, but just written differently using these curly set brackets and then coordinates inside of it. Or they could be an equation. So this is an equation of a circle, but any type of representation can be a relation. Now, what is a function? A function is a special kind of relation. A function is a relation from set A, which we call the domain, to set B, which we're going to call the range, that assigns each element in set A to exactly one element in set B. So what that means is if we have something in the first set in the domain, it can only go with one thing in the range. If you have a relation that has something in the domain assigned to two different outputs, two different parts, two different things in the range, we don't consider that to be a function. It's still a relation, and it can even have an equation, but it's not a function. So you can look at here, which of these two mappings shows a function? So if you think it's this one, type a 1. If you think this one, type a 2 in the chat for me. Which one is a function? Okay, 1s are popping up, which is good. 1 is the correct answer. 1 is a function because every single element in our domain only is assigned to one thing in the output, right? The number 1 only goes with 4. The number 2 only goes with 3. The number 3 only goes with 4. There is a common output, a common number in our range that 1 and 3 both go to. That's not a problem. That's okay, right? That would be okay for a function. It can't go the other way, that one thing in the domain goes to two different outputs, which is a problem here. The number 1 goes to -2 and 2. That's a problem. I like to think about a function literally like a machine. If this was, let's say, a soda machine or something, and you pressed in the number 1, but you didn't know what you were getting out. So you pressed to get a Fanta, but you didn't know if you were going to get a Fanta or water, right? That wouldn't be functioning properly. It would be a pretty bad machine because for one input, you don't know what output you're going to get. So this one, not a function. Okay, what do functions look like? So functions as graphs have a really, really quick test for them. So same as relations, we can have them we can have functions look like any of the same things that relations did. They could be mappings, tables, graphs, ordered pairs, equations. But in particular, graphs are really easy to decide if they're functions. There's something called the vertical line test. So which of these two things is a function? Type of 1 if you think this is a function. Type of 2 if you think this is a function. Seeing a lot of 2s, and that's absolutely correct. So what we have here with these blue dashes, these are our vertical line tests happening, and this one is not a function because we have a vertical line here that intersects the graph in 3 spots. Really, we only care that it was more than once. This is not a function because this x value, this part of our domain, is related to 3 different y values, right? Or there are 3 different points on our graph that have the same x but different y, same input, different output. Whereas on this one, no matter where we draw the vertical line, it only hits 1 time. So every x value is associated with only 1 y value, or related to only 1 y value. So it is a function. That's called the vertical line test. I already talked about it. Seems like you guys already know about it. I'm good to go. Sometimes on graphs, it can be hard to tell. This one is pretty easy to tell, but if a graph maybe has like a vertical asymptote, it's a little bit difficult to tell if maybe there is a vertical line there, but we do know with vertical asymptotes, that doesn't affect it. It is still a function, or at least it's not a function because of a vertical asymptote, because those points get infinitely closer to the asymptote. They don't just go straight up and down at any point. Okay, so how to decide. Here's a quick kind of summary of how to decide if a particular relation is a function or not. So in general, you can just look at the points or the x's and y's and make sure that every x has only 1 y. So every element in our domain, our input set, only is related to 1 element in the output set. So for a mapping, again, you can just sort of look at that. And for a graph, you can always just use the vertical line test. But for an equation, it's harder, right? If we have an equation, we can't necessarily tell. Well, we can, it just is a little trickier. There's a little bit more to it. So we're going to look at these 2 equations, and I'm going to go over them really quickly. We could use what we know about a particular type of an equation and what kind of graph they make, and then use that to help us. So that actually is useful for the second one. Or what we can do is we can solve these equations for y. And as long as they make it so that no matter what x we put in, we only get 1 output, we're going to be good to go. So let's just kind of see what happens when we try to solve this first one for y. So I'm going to go over here. So if I'm trying to solve this for y, I need to get everything that's not the y over to the other side. So I can kind of do that pretty quickly. So I need to move that over. So it'll be negative 6x squared. I'll move that one over. It'll be negative 4x. And then I'll still have a plus 10. And then the only thing left here is just to divide everything by negative 2. So I divide this whole side here by negative 2. So I end up with y equals negative 3x squared plus 2x minus 5. All right, so we can use a lot of different...
3x squared, I think.
Oh yeah, my fault. Thank you. We will just kind of scribble that out. Yeah, good catch. It won't matter in particular for the question I'm trying to answer here, but it is absolutely incorrect for me to leave that as a negative 3x squared. So thank you for catching that. So we can use what we know about what kind of graph this would create. Well, this is a quadratic equation, x squared plus x plus, plus or minus a constant. So we know this is just going to make a parabola, right? And we know just vertical line test, this would for sure be a function. So we could do it that way. We could just kind of look and see what equation we end up with. As long as we understand what types of equations create what types of graphs, we could kind of do it this way. The other thing we can do is just kind of think about as we put in numbers for x, is there any way that I put in a number for x that I could get 2 different outputs? Well, no. when I put in 1, I do my calculations here, I'm only going to get one number out. There's no way for me to get a second output with this particular equation, so, well, this one is a function. On the second one, a little bit different, is as I go to think about this, I could recognize that this is the equation of a circle. And we know that a circle, well, if I graph a circle, it would fail the vertical line test. So we know it's not going to be a function. It's a circle with a radius of 5, if we remember that. This is my radius squared, centered at the origin as well. Again, if I knew that, that's great. I can answer that question really quickly. The other thing I can do is to solve this for y. So if I do that, moving things around, I could end up with this. Move the x squared term over, right? Subtract it from both sides. And then taking the square root. But we got to remember, when we take the square root of something when we're solving, so in this case, we're solving for y, we have to remember that we actually get two different things. We get a positive and a negative root. So this is the positive and negative square root of 25 minus x squared. And here is where we actually get two outputs. When I put in the number 0, for instance, right? I plug in 0 for x, I end up with the square root of 25. But because of this positive and negative, I'm actually going to get two outputs. I'm going to get positive 5, which would refer to that coordinate up there, and negative 5, which would refer to that coordinate there. So the number 0 as an input is actually associated with two output values, so this one would not be a function. Really, the only time we're going to obviously be able to see this is when we have radicals. Radicals are going to be really common. There are other couple types of operations that might give us repeated outputs, some trig functions when we learn about them and some other things. But really the thing we're looking for is when we take the square root to solve and we have to consider the positive and negative root, that's going to be the big issue. And that's what's going to give us the two different outputs, thereby making it not a function. Okay. I don't want to go too fast, but I do also want to make sure that I'm covering as much as we can here. Are you feeling okay with everything that I've said so far? I'm hoping a lot is review. All right. Let's do this. If you are feeling good about things in chat, just give me a yes, you're ready to move on. Or you can actually use the, in the participants window, use the like yes or no, like yes, I got it, and I'm ready to go, on. Cool, looks like a lot of people are good with this. Yeah, again, I'm hoping a lot of this is review, some things you've talked about before with maybe tiny little new things sprinkled in. All right, so evaluating a function, again, this is another thing that I'm pretty sure everyone can already do. We're gonna amp it up a little bit, make it a little more complicated. Maybe not necessarily more than you've already done, but just it's not just plugging in numbers all the time. So evaluating a function is when we are determining the output of a function based on a particular input. Now, the input of a function can be anything that we want. It could be a number, it could be some sort of algebraic expression, it could be another function, it can be all kinds of different things. We can evaluate functions using a mapping or using a table or using a set of ordered pairs or graphs or equations. Most of the time, it's going to be equations. We're going to have an equation, and we're going to evaluate that equation form of our function for a particular input. Yeah. So let's go ahead and look at this function here, and go ahead and try this, because I'm sure you can all do this pretty easily. So evaluate this function for these two things. And I'll give you a second to get ahead of me, and I'll start. As I change the screen on you. So for this one, pretty easy. This one is -4 plus 8 plus 1. Just making sure we follow order of operations, but we can do things simultaneously as long as they don't conflict, right? We can do the exponent and this multiplication because they're not actually conflicting with each other. And then add these all together, and we get a pretty simple output of 5. Yeah. So formally, we would write that f of 2, the function with an input of 2, gives an output of 5. Here we're putting in an expression, but again, it shouldn't be too difficult, just a little more complicated in terms of actually evaluating it. So I'll get that started. We're going to do a lot of this, so it's real important that we can kind of do things like this fairly quickly, plugging in expressions into functions. So again, I can kind of do this part and this part both in the same step because they're not really going to directly conflict with each other. I do need to be careful about this negative because I need to square this and then distribute a negative to everything, apply a negative to the whole result. So when I square that, I get x squared plus 4x plus 4 plus 4x plus 8 plus 1. And then again, remembering this negative, I need to distribute it. So and then once we're at this stage, it should just be about combining like terms accurately. So we have -4x and +4x, so those can go away. We have let's see, so writing this all out, we want to simplify as much as we can, -x squared, and then -4 plus 8 plus 1, that's another 5. And again, we formally, right, we say the function with an input of x plus 2 is equal to that. This is stuff that you already know how to do, but just making sure we touch on it and give you a chance to kind of practice it as we go. All right. So piecewise functions, I'm not sure how comfortable people are with what a piecewise function is. I've got a graph and an equation written up here, but basically a piecewise function is a function that's built from pieces of other functions, where each piece of the function only applies to some interval of our domain. So here we have this function f of x, which is created by 3 pieces. We have this function x plus 3, but we only apply that function if x is less than -2. So that's this here. So if x is less than -2, we apply this particular function. And then we have the second piece. We have the negative absolute value of x plus 5. We only apply that piece if our x value is between -2, including -2, all the way up to 3, not including 3. And so that's our blue section here. That's that little piece of our absolute value graph. Notice how we got a closed dot there because we are including when x is -2, whereas we had an open dot right here because for this piece we weren't including when x was -2. And then we have our final piece if x is greater than or equal to 3. So we have, again, a closed dot because we are including that particular endpoint, and it goes forever, it goes on forever. So a piecewise function is just a function that's built of multiple other functions as pieces, and they each account for a particular interval of our domain. Generally, all numbers should be included here, and there shouldn't be any overlap, right? And in this case, there's not. From all the negative numbers all the way up to -2, not including -2, we use this one. From -2 to 3, we use this one. And then from 3 on, we use this one. So everything's covered. There's no gaps here. In general, that's the way it should be with piecewise functions. So no overlap, nothing missed. So let's look at an example of a piecewise function and evaluate it. So evaluate the following piecewise function for these 2 numbers. Again, these are numbers. For piecewise functions, we kind of need to use numbers. So take a minute, get started on that. See where you're at. So sorry to talk over you, but major first step is to figure out what piece to use, right? So if my input is a 3, I need to figure out what interval of my domain that falls under. And so 3 is not less than -10. It's not between -10 and -2. And okay, it is. It is bigger than -2. So I would make sure to use the third piece on this one. 3 to the third power. All right, so quickly simplifying that, we get 27 over 12, and then because it's a fraction, we would like to simplify that. They're both divisible by 3, which makes this 9/4. Pretty easy. Again, simple evaluating once we figure out what piece to use. The only time where I see a lot of tricks with this is when we have numbers that are kind of on the border. People get confused about which one to use it with. So you want to make sure if it's a number that's on the border of our intervals, we need to pay attention to which piece it actually should be going with. So for -10, well, which one is it in the first piece or the second piece? We need to figure out where is it included, right? So we're looking to which one has the or equal to option, right? So this piece includes -10, whereas this one goes all the way down to -10, but doesn't actually include it. So for this one, we would want to make sure to use the top, the first piece of this function. So again, once we identify that, it's a pretty simple process of just evaluating it using the appropriate piece. So we end up with 100 plus 50. So we get an output of 150. But again, if you use the wrong piece, right, if you use this piece, -10 plus 19, you would have gotten 9, and then, that's not the right answer. You're evaluating this piece correctly, but it's not supposed to be used with that particular number. Okay. Piecewise functions. All right, domain. This is one of the things that I know you talked about last year, but it also is just one of the things that students traditionally have a difficult time with. So I know over this section, we're going to briefly touch on it, and then most of section 1.2 really gets deeply into what domain is. But the domain of a function is the set of all values of the independent variable, the input variable, for which the function is defined. That second part is really important because some functions are what's called undefined for certain input numbers, because in math there are some issues. We can't divide by 0, so any input value which would cause us to divide by 0 would be considered to be undefined. Or another thing is when we try to take the square root or any even root for that matter of a negative number, again, that's not defined. Technically, we could talk about imaginary numbers, but when we're discussing a function, unless we really want to include imaginary numbers in our range, generally we say that it's undefined at any value that would cause us to take the square root of a negative. So we have to be, those are the two big things we need to be cognizant of when we're looking at an equation or of a particular function. We're looking for anything that causes us to divide by 0, or anything that causes us to take the root, even root in particular, so square root or fourth root or something like that, of a negative number. Those things are issues. So as we look at this example, what input values, what numbers would cause a problem with this function? Go ahead and type in something that you see. What number would cause a problem with this function? It's funny because in the chat, I see one of the answers just like all up there. Yeah. 2. 2 for sure. Is 2 the only option? Is 2 the only problem? -2. Yeah. So both of those numbers are an issue. So for this particular equation, we would say the domain is undefined for these two values. So sometimes when we're writing out, there's so many ways for us to write out domains, but a simple one, we would say like domain is, oh, I go to write and then turn on my annotations. So we'd say the trying to be patient with my own abilities here. Okay, going back, annotate, draw, got it. There are many ways that domains can be talked about. They can be written out formally or not. So we might say something like all real numbers except x equals 2 and x equals -2. Or you could even combine that to say except x equals positive and -2, right? You can combine that together. Other people might say the domain is x is not equal to plus or minus 2. So anything that's not equal to plus or minus 2, we're good. There are many different ways that it can be written for this type of domain. In general, if you weren't sure what values right away would work, anytime you have a fraction with a variable in the bottom, what you can do is you can take that denominator and you can figure out the domain or the excluded values from the domain by just solving an equation, right? We can say, what is going to make this 0? And we just solve it. So we add 4 to both sides, take the square root, and we end up with x equals plus or minus 2. So these would be our excluded values. And that works anytime we have a fraction with variables in the denominator, because any number for x that would cause the variable to the denominator to become 0, that's a problem. We consider it excluded. We can't let it in the domain. Okay, so I kind of summarize this here on the next slide. Okay, so the domain of a function equation. Shorthand here, basically anything that makes the denominator equal to 0, so denominator can't equal 0, we call those excluded values. And then anything that causes the square root or a square root in the equation to try to take the square root of a negative value, that would be a problem. So just kind of quickly, I could come up with an equation for us here on the second one. Let's say we had a function that was like f of x equals square root of x plus 2. Well, I could think about it pretty easily and say, all right, well, -2 would make this a 0. So that would actually be okay. We can take the square root of 0. But -3, that would be a problem. That would cause us -1, and we can't get a real number there. But the real shorthand with this, the easiest way to do it to figure out your domain is you take what's inside of your radical and set it up with this inequality. So we would say that x plus 2, this has to be greater than or equal to 0. And that will establish our domain. That doesn't talk about the excluded values. That actually talks about what is in the domain. So I solve this, subtract 2 on both sides, and I say, all right, well, as long as x is greater than or equal to -2, this would be our domain. It's a pretty simple process. Again, we just take what's on the inside of the square root, and we say it has to be greater than or equal to 0. Greater than or equal to 0 is just another way for us to say that it's basically positive, right? Or maybe rather not negative. Because technically 0 is kind of in the middle. It's not positive or negative. So really what we're saying is that greater than or equal to 0 is the same thing as saying not negative, which is the problem with square roots. We can't take the square root of a negative and get a real number. All right. 3 minutes remaining. Made it farther than I thought. Let's have this be the last thing we do. So take these two equations. We didn't quite finish, but that's okay. There is a homework assignment over 1.1 that you can find later on the slides. We didn't get to the very last piece. So this will be the last thing we get to today, and we'll pick up right here tomorrow. And again, I'm just trying to get a feel of how far we can actually get in a day. We'll see. And I'm sure this is something you guys talked about in Algebra 2 also. I'm not trying to say I would expect you might have already been able to do some of this stuff, but so for our first equation here, again, the big issue is we have a fraction with a variable in the denominator. So we got to be careful. Anything that would cause this to be 0 is an issue. So if it's a real simple equation like this, we can just kind of jump into it and say, well, that's really easy. I know the number 7 is an issue. So we could just say our domain is going to be x is not equal to 7. And that's the only number that's a problem. It's pretty easy. If you weren't sure, just set up the equation. If this was like a big polynomial that you would have to factor in order to find the particular roots of it, you know, you would probably want to set up this equation and factor it and solve it and everything. But in this case, pretty simple. I don't expect you to have to do that, right? So x equals 7 is our excluded value. This one, only slightly more complicated. I kind of touched on it, right? Anything inside the square root, right? We just need to make sure that this is not negative, right? This has to be not negative. And our sort of proxy mathematically for that is greater than or equal to 0. That's the way we write that sort of mathematically. So we can establish our domain by simply solving that. That what's inside my square root got to be greater than or equal to 0. Pretty simple inequality to solve. We add 1 to both sides, divide by 5, and we're done. So this would be our domain. Okay, so I'm gonna go ahead and flip to the homework page just so you guys can see that, and I'm gonna post it on the Google Classroom page. I just got a little busy this morning as I was kind of finalizing things, so it will be on there, but I'm gonna get to it now. And we just missed that part. So this is the homework page. I'll clear that. You won't be able to get through maybe some of these down here, the difference quotient. We didn't quite get to that, but again, we'll cover that tomorrow. So I posted a PDF version of the textbook on the Google Classroom page that you can use. It's just 1.1. If you've already picked up your textbook at UHS, obviously you can do that. If you haven't picked up your textbook, they're all there in your boxes. You just go to the Iowa Street doors anytime, like 8 to 4, I think they can be picked up. Just let them know you're there to pick up your stuff and what your name is. Sorry for holding you. Go ahead, you guys can go ahead and go, get ready for next class, and we'll pick up where we left off tomorrow.
Hey, Mitchner.